The double-effect absorption cycle is created by adding two components to a single-effect absorption cycle, a high-stage generator and a high-temperature heat exchanger. These components operate at higher pressures and temperatures to increase heat transfer, mass transfer, and absorption cycle efficiency. They work in conjunction with the original single-effect components, now renamed the low-stage generator and the low-temperature heat exchanger. In the double-effect cycle, refrigerant vapor is released in both the high and low-stage generators for a given amount of heat input just to the high-stage generator. A double-effect cycle, therefore, requires less heat input to produce the same cooling capacity as a single-effect cycle. This cycle has a coefficient of performance of about 1.20, compared to a COP of 0.70 for a single-effect cycle. How is this possible? Let's compare the cycles by looking closely at the differences in the double-effect cycle. Let's begin at the low-temperature heat exchanger, where the flow of weak lithium bromide solution is split. About half flows to the low-stage generator, and the rest flows through the high-temperature heat exchanger to the high-stage generator. Inside the high-stage generator, the weak solution is heated by a steam coil or other primary heat source. Heat from the steam boils refrigerant vapor out of the solution, making it a concentrated or strong solution. The strong solution flows back through the high-temperature heat exchanger and is cooled by weak solution going the other way. It is then joined by the strong solution leaving the low-stage generator. The combined strong solution flows through the low-temperature heat exchanger, is further cooled by weak solution, and then flows back into the absorber through the spray nozzles. Refrigerant vapor generated by heat input to the high-stage generator maintains high stage pressure at approximately 24 inches of mercury, which corresponds to a condensing temperature of 200 degrees. The higher pressure refrigerant vapor flows from the high-stage generator into the tubes inside the shell containing the low-stage generator and the condenser. Here, three things happen simultaneously. Inside the tubes, the vapor condenses to liquid as it releases its heat of condensation to the weak solution that is spraying over the tubes. The liquid refrigerant then flows to the low-stage condenser, where it is further cooled by being sprayed over the cooling tower water tubes. The heat released by the condensing refrigerant vapor boils refrigerant vapor from weak solution being sprayed over the tubes, reconcentrating it, making it a strong solution. The boiled-off refrigerant vapor migrates to the condenser, where it is condensed to liquid by cooling tower water. Strong solution flows from the low-stage generator to join the strong solution from the high-stage generator. This combined strong solution flows through the low-temperature heat exchanger back to the absorber through the spray nozzles. Liquid refrigerant from the low-stage generator mixes with liquid in the condenser, then flows from the condenser through an orifice back to the evaporator sump. The key to the double-effect cycle is establishing a higher pressure and temperature level in the high stage. By raising high-stage condensing temperature to 200 degrees, well above the 170-degree solution temperature in the low-stage generator, heat can be transferred from condensing refrigerant to the solution. This concludes our section on double-effect absorption, a non-mechanical vapor compression refrigeration cycle. Please take a moment to complete the following learning activity. To continue, make your selection.